every time I open Pop's Patreon questions file, it has more and more text in it. It's got more and more questions.
Yeah.
You want to start with a random question I got here from yesterday? You want to jump right into it?
Let me cover a couple things and then
we're never getting to it then.
No, we will. Don't worry.
It's a quick question.
Oh, it is. Well, no, we can.
No.
Probably.
You don't have to go into details. Just off the top of your head, do you think there's more thread dedicated to particles, like the atoms, or is there more thread between particles as light? Which one do you think? Where do you think the resource goes?
Oh, I would say it's more in light because light is all over. I mean, you have light coming from just about every
across the entire universe.
Yeah, just imagine light having to travel. You know, the torsion having to travel all the way from one galaxy to another. You know, it's just all space.
Or just imagine from one edge of the universe to the exact opposite edge.
Yeah.
That's a one uninterrupted rope. What do you think the length of that motherfucker? What's the length of the universe diameter? What's the diameter of the universe? Because there's one rope there.
Okay, 3, 2, 1. Let's go online. And hello, everyone. We're discussing here with Hans. He's on the other side here.
Hi, guys.
And we're discussing about whether there's more rope making the atom, all the atoms, obviously, all of matter, or is there more rope building light? You know, the rope that interconnects atoms. And my guess is there's more light than atoms, or more rope dedicated to light than to atoms. Something wrong?
No.
Sound?
No, that's fine.
Yeah? Don't scare me. Anyways, yesterday we left off. We've been dealing with the neutron this week, and yesterday we left off with this little image here, donut, okay? And I'm saying that just maybe, okay? You got to think of maybe that's what the electron or the magnetic thread is doing when it surrounds the electron. Maybe it's moving, you know, like on itself, just twirling in situ, and probably rotating as well. But I mean, that's maybe something like this is happening at the electron shell for every little magnetic thread. So if you can visualize that, maybe this helps you get a picture of what the atom might look like. And the other thing I had mentioned at the end, which is very important to keep in mind, is that the electron shell is not smooth. Okay, looks like a ball of yarn. Looks something like this. Here's Mr. de Broglie. And Louis de Broglie, he won the Nobel Prize, I can't even remember what year, but I think in the 1920s. And that was because he came up with this idea that the electron shell, or cloud, which they deny, they just say it's a little electron that's moving back and forth, up and down like a wave. They're saying that that's what the electron is, that it's not only a particle, concentrated particle, it's also a stretched out wave. But that wave, according to de Broglie, stretches all around the atom. And the important thing is that it stretches out in integral waves. In other words, in integral links under the rope model. If you count those, you'll find that there's there's a fixed number. There's never a half a wave or a quarter wave.
There's no such thing, is there?
Well,
it doesn't matter where you cut it off. It just depends on what angle you're looking at it from.
Well, all he was saying, I guess these people don't visualize these things. They just go with the math and they say, look, this is the calculation, and he came up with the fact that, you know, these are integral waves. Under the rope model, no problem whatsoever. What you have is simply a link of the rope, okay? It's straightforward.
Yeah,
and that
one weird thing that I was mentioning with that is a link is a link depending on where you're looking at it from.
Where you're looking at it. Well, independent of observers,
No.
there's
What I
a
mean
link
is,
there.
there's no such thing as a link in a way of speaking, because
How about this? Isn't that a link? Hold on, let me pull this down so people know what I'm showing here, you know. Hold on here. Here's a rope. Here's a link. I would say, yeah, there's one link, right?
but if you turn
You want
it,
me to show them that way?
but if I look at it from up here, now it's not a link.
If you look at it from up there.
Because now it's further down.
Well,
you know what I mean?
Well, yeah, okay. That's
thing.
what you're. No, what I'm saying is, as far as Mother Nature's concerned, she doesn't have observers. What we're saying is, you know, at some point there's a starting point and an ending point. But what we're saying is, you don't have this, or you don't have this. That's what we're saying. Okay, so you won't
Yeah,
have.
but you know what I mean. There's no such thing as a link.
Right. I see what you're saying, but you know, from Mother Nature's point of view, again, there's no observers, there's no perspectives. And so, you know, you just look at a link and it's a full link in a sense that you're never going to get half a link. You're never going to get a link and a half. You're always going to get one link. In other words, if we count the number of links around the electron shell, it's a fixed number. It's an integer. You're never going to end up with 20 and a half or whatever, you know.
What do you mean by links around the electron shell?
Yeah, imagine this. This is the rope around, right?
Coming out of it?
No. Listen. The rope forks out, right, at the boundary of the electron shell, and one of these guys goes around.
Okay.
But when it goes around, it doesn't go smoothly. This is what this picture is showing here. The ball of yarn. If you look at the ball of yarn. The electron, and that's the image on the left there, lower left. The electron, what should we call it? Should we call it the shell? De Broglie dealt only with 2 dimensions here, and he's saying, you know, it's like a little string that's pulled all around the electron, forming the electron shell, but that string goes up and down. It's got bumps. It's goosebumps all around. And so if you go all around, you always end up with an even number, not an even number, but an integer number, right? Of links, of snake bendings. You know what I mean?
How do you have half a snake bend?
Well,
what does half a snake bend look like?
Just imagine this. And again, let me put the image here so they know what we're looking. It's better to do it not with a rope because rope is confusing. I would need a
cable.
Yeah, any cable. Do we have? I think I have some here. Hold on. One of these has. Let's see if I can do it with a rubber band. Pretty big rubber band, and you know, you got something like that, right? It's just a single guy right there, right?
Okay, you're trying to make the S.
I'm making an S, okay?
I get it.
And what I'm saying, you never get half an S.
Okay.
And when you go all around, you end up with 20 S's. You never end up with 20 and a half, 20 and a quarter, you know. And that's what de Broglie showed, and that's what they gave him the Nobel Prize for showing that. And this is the electron. We're not talking about light. We're talking about, he's saying the electron somehow moves as a wave around the atom. And we're saying, no kidding. It's the electron shell. It's built of, made of the magnetic threads that go around. And yes, we can imagine them, you know, going like a snake around. In other words, they're not smooth. They're not, let me again use that. They're not smooth like that. They're going to be like that all around, right? And when you count all those little S's all around, it's an integer number. And that's what de Broglie demonstrated mathematically. And there you do have to give these guys credit, right? Okay, so that's so once again, here's the ball of yarn. That's how we have to imagine the electron shell, something like that. In other words, it's a rough surface. It's not a perfectly smooth surface. If we had the eyes of God and we could get it, you know, to see an atom, a hydrogen atom, it would probably look more like that than a completely smooth surface. Okay. And okay, so there's an explanation there, or a description. An electron standing wave, remember standing waves, okay? Vibrating in an orbit around the nucleus of an atom. Isn't that the description of the magnetic thread going around there? I mean, that's exactly what they're describing now. An electron standing wave, right? That's our magnetic thread vibrating. It vibrates. Maybe it also turns, like I just showed with the donut, okay? In an orbit around a nucleus of an atom. And obviously this is not orbiting, it's the hula hoop that surrounds an atom. Okay, and again, I guess they're just looking at one cross section. They're looking at just a belt that goes around the atom instead of looking at it as a sphere. But de Broglie was conscious, and it really came up by, I think it was 1926 that Max Born came out with this idea. Maybe later, maybe 28 or 29. He came up with this idea that, you know, that the electron is really like a shell, like a cloud, the cloud model, like a cloud that encapsulates the nucleus. But he says what it is, the way they imagine, is just a little electron bead at many places at once, at least more than one place, okay? More than, in other words, at least two places, right? Okay, and then we have there the other description. Only integral numbers of wavelengths are allowed, okay? And so, okay, he showed that. That's one of the things that gives an image of what the hydrogen atom might look like. If we had the eyes of God, we could go down there and see it. At least we could see the outside of it, and it would look like a ball of yarn. What do we need to explain about neutrons? Well, the main one that I guess got everybody rolling was this beta decay, beta minus, beta plus, and that's that a proton converts into a neutron in the case of beta plus decay, and neutron converts to a proton, and that's the beta minus, okay? And so assuming that what these folks saw, and we concede this, how do we explain it under the rope model, okay? And that's one of the things we have to look at. And I explain it here. Let me show you my version one more time. This is my version. Here we have the rope, we have the neutron. It converts into an electron shell that encompasses the proton dandelion in the center. Now it's pumping, quantum jumps there. And now this one, 15 minutes later, can turn back into a neutron, which has no charge because it's just a convergence of ropes that carry signals from one place to another. And obviously there's been a lot of questions here, you know, and I'll just make a comment on that. You know, first of all, we're in a brainstorming stage, okay? Let me get that out. We're in the brainstorming stage. There's still a lot to brainstorm, especially with respect to the neutron, especially with respect to neutron decay. And some people might say, well, you know, I guess there's no answer to this, so the rope model really doesn't fly.
And the problem is the opposite. It has too many answers.
Well, some answers are very difficult. And, you know, I told my son, I've told several people out there that for me, you know, what was called light on light, this problem light on light, which means light goes through light, was a major problem. It was a major problem for me, and it took me 2 years to figure out an answer I could live with. And still, I can live with it, but it's one of those things where you say, well, this is really more like magic.
What's it got to do with the neutron?
It's got to do with the neutron in the sense that the neutron also appears to be magic. You know, some things that we cannot explain now.
Oh, why?
Well, like, I mean, you know, how does it move? Does it carry its center with it? Or
you can imagine all this. They're all imaginable.
They're imaginable, but we still have trouble answering how, you know, how a neutron moves, how it converts or decays, you know, into an atom and backwards.
I think it's more like we have many answers, and we just haven't delved enough into the issue to kind of put our hand in the fire for one of them.
No, but it's not only that. Keep in mind something else. You don't want to say, oh, I know what it is. It's this, right? And so you go with this. It turns out that this violates some other property. You got to keep all these properties like simultaneously and say, okay, if this here, we can see this one here, well, how do we explain this one over here? Because now we've changed something that this one can't handle, this other problem can't handle. And so you got to be careful when you move things around, because you trouble
the assumptions that you take on board. But so far, I haven't seen any magic with neutrons yet.
Well,
not on the level of light on light, at least. That's serious magic.
Yeah, that
is. That has to do with superposition, because also when you talk about the neutron, when the atom becomes a neutron, right? Just that transition, the electron shell collapses, and somehow, without breaking, it superimposes, goes through itself to reform into threads.
Yeah.
That's magic. But it's using the same superposition magic that light on light uses, this notion that threads can go through each other.
Yeah.
It's like that's just kind of a ground rule that you can fix all these magical properties.
Yeah, you have to, let's put it in different words. Using Occam's Razor, we have to make the least number of assumptions, a lot less than quantum mechanics or mathematical physics in general. In other words, we do not have to use concepts, move concepts around. We don't have to talk about energy. We don't have to talk about time. We don't have to talk about mass. None of fields, none of those things. We don't have to invoke concepts. We're going to be doing this with objects, which maybe a lot of quantum people would say, well, you're doing this with classical mechanics. Well, kind of yes. We're doing it with rocks, we're doing it with stones, we're doing it with trees, with dogs, with houses. We're doing it with normal things that we can imagine of everyday life. We can do it with wires, rope, obviously, strings, balls of yarn. We can depict Mother Nature's invisible universe with things of ordinary life, at least the shapes. Obviously, they have different properties at their level, but it's all imaginable. Quantum mechanics is unimaginable. They can't imagine. You can't imagine energy. You can't imagine field. What is field? And what is time? You have to explain. Well, let me tell you what time is. No, make a picture of it. What do you got to put on the board?
About imagination, where the superposition light on light thing that you bring up, it's still imaginable. In the sense that I can imagine two ropes going through each other, kind of like in movies. It's not. We're not just using words for some placeholder thing that we're not even sure what to even look at. With the superposition, we know clearly what we're imagining. The magical part is when they cross each other. We can imagine it, but it's not rational. It's that area where
what is that? That's one
frame where they exactly pass each other. I want to know what's the detail there, and there is no detail. It's just.
That's one part. Then they have also superposition and particles at two places at once.
But that's different. There's two different types of superposition, because we use superposition with light on light. Where we say two threads can occupy the same crossroads essentially.
Right.
They can go through each other. At one point, they occupied the same spot.
You would think.
But the other superposition which they use is just completely bananas, which is when they say one thing can be in two places at once. Okay, now you lost.
It's called decoherence.
Yeah, you lost. That's
so we invent.
It reminds me of the Joker from Batman when Batman was asking him, where's the girl, and the Joker was giving him like a time, and he's like, well, what does the time matter? Well, depending on the time, she'll be either in one place or several, implying that she's gonna blow up.
That's quantum stuff. And see, all these people say we're not doing science fiction, we're doing science. See, because quantum tells us that a particle can be at two places at once. So that's and then the other one is that if we concede the concept and we concede particles being at two places at once, let's concede all that. Let's just give it to them. How do you produce attraction, with particles? And so they don't have a mechanism. They cannot offer you a physical mechanism for attraction, especially for attraction. Pushing is no problem. Two particles pushing each other, everybody more or less can visualize that. We've seen push everywhere. But now, how does a particle pull on another one? Now there you're going to have to use magic, bring angels or spirits or whatever. And so, you know, quantum mechanics has lots.
I got Occam's Razor here in Wikipedia. Occam's Razor is a principle from philosophy. Suppose there exists two explanations for an occurrence. In this case, the one that requires the least speculation is usually better.
Yeah, and what we're saying here is that the rope hypothesis is not clear-cut yet. We're still, you know, brainstorming many things, but
because it takes a lot of brainstorming to figure out which one is the one with the least amount of weird assumptions.
Yeah, but we're already starting very simple, because keep in mind, how simple can you get? We're saying there's a single thread in the entire universe. At least our universe. Maybe there's a parallel universe, but we're not going to concern ourselves with that. That would be speculation. But, you know, the matter that we see and that to which we belong, that group of matter, we'll call that the universe, it's comprised of a single thread. Now, that doesn't get it any simpler than that. And this thread is an elementary entity. In other words, it's not made of more basic building blocks. That is the building block of everything else. It's called the electromagnetic thread, or the thread. We call it the single thread. And once you give the single thread, even what comes after is quite simple. This thread just turns into into atoms and neutrons. We might question, I think a couple people have questions about the neutron, but I can only give you my version. That's that there are neutrons, there are atoms. That's it. That's all there is. Atoms are, you know, you have different levels of atoms. Atoms that have been crunched inside the sun, have blended into bigger elements. Fine. But the bottom line is, if we just talk about hydrogen atoms, then all we have in the universe are neutrons and hydrogen atoms. And these hydrogen atoms blend with neutrons, make bigger
Helium,
elements.
Helium, for example, which is two hydrogen and two neutrons.
Right, and you can keep building on that all the way to uranium.
Or people, or buildings.
Yeah.
But what I like about that is you start at the bottom and go up. They start at the top and go down. They split the particle into two more basic particles, split those basic particles.
End.
And they go down, 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 down. That's the wrong way of going about it.
They keep smashing
particles. Theoretically, if you wanted to figure out what is the universe made out of, you start with the bottom. You kind of propose, okay, what does the very basic,
your
by
hypothesis,
definition,
your
cannot
ground
be
rule.
split up.
Yeah.
At some point, I mean, I think anyone has to concede that. I mean, you'd think there are probably some people that don't, but I would consider people normal. that at some point they say, okay, at some point there's something you can't split up, right? Or else you go insane. You can't keep what? Can everything be split and split and split and split and split? And if you keep cutting the banana in half,
you end up with more bananas. Always with a banana.
Like at some point, can you say that you cannot cut it in half?
And that's the problem that quantum has also. Quantum talks about elementary or fundamental particles or entities or whatever you want to call them. But those are only temporary, because they say, look, we found the elementary particle that makes everything else, and let's call it the quark, just for the sake of argument. And then the reporter says, well, what is a quark made out of? And so the guy says, well, let me smash it and let's find out. So until today, it was an elementary particle. Now they smash it and they find out it's made out of gluons. So let's assume that, right? So now they got gluons. And now the reporter comes in again and says, well, what is the gluon made of? And the guy says, well, let me smash it and I'll tell you tomorrow. And so they keep smashing, breaking up, seeing little lines in their chambers there. And they say, well, I didn't see this squiggly line before. I'll call that Johnny. And so next time he says, well, we found a gluon and it's made out of Johnnies. It just never ends.
Is it an assumption to say that there is something that cannot be cut? Is that an assumption? Does that count as an assumption?
You would think that is a fundamental assumption of quantum. It's a predictable assumption.
What?
There has to be a something that comprises everything else, and they say we're still searching. You know, they have job security until the end of time because they keep searching. Whenever they find something, oh, we found the elementary particle. today.
Yeah, okay, but
today, temporarily.
For now, yeah. But then again, does it count as an assumption to say there is something that cannot be split?
You would think
does that count as an assumption?
You would think that that's a principle. Should be a fundamental principle of quantum. They should come up with that principle. Not all this nonsense.
Quantum, but science,
well, let's go with quantum because that's their realm, right? Quantum, instead of having all these idiotic principles like uncertainty and complementarity that are idiotic, they're really idiotic principles. They should have another principle, and the principle should be the one I'm going to, pronounce now, and that is that there must be, no matter what, there must be an elementary particle, a particle that cannot be broken into further constituent parts. It is the building block of everything, of gluons, of quarks, of atoms, of pions, muons, whatever's out there. There should be this particle. And that's the one they've been searching. And instead of arriving at that little guy, what they've done is balloon. We have over 200 particles in the quantum world. In other words, they've created names, 200 names for different types of particles. That's the number I heard out there. I've never counted them, but yeah, you'll find solitons. Oh, what's a soliton? Well, it's a particle that looks like a wave. And, I mean, they have the tachyon comes from the future. So faster than light, it comes from the future, and so on.
Are there assumptions that are kind of more than assumptions, kind of unquestionable assumptions? For example, if one thing pulls on another, there's something mediating that pull.
That would have to be a principle.
But yeah, but that falls under the same. That's what I'm saying. It's like it's more of an assumption. It's an unquestionable assumption where we go, okay, come on, let's not question that one, guys. Let's not get too weird.
I think that's what the word principle means or should mean.
Okay, but then there is a fundamental building block that cannot be split. Would that assumption fall under a principle instead?
I would say that should be a
principle. You would
categorize
it as a principle.
I categorize it as a principle. Like I have my golden principle, which I use that quite a bit. The golden principle is you can't do physics without objects. And anyone who questions that is an irrational person.
Yeah, but that's talking about the rules of physics. But
that is a principle.
No, because that's the rules of physics. Because another rule of physics is you're only going to speak literally, no metaphor. Well, no, that's how we're doing it.
No, but hold it. You keep that in mind because people, there's probably a lot of religious folk that are going to question that, and they're going to say, well, why do you need to do physics? Physics, I'm saying that's a principle of physics, like number one principle, golden principle, mandatory principle. And someone might question that and say, well, I don't agree. I don't think you need to have an object to do physics.
Yeah, but you're talking about the rules of physics.
No, but it's not. It's like it's the starting point. It's a principle.
I'm talking about the difference between how you do physics or what you call physics and the assumption. Once you're doing physics, there are basic assumptions that cannot be questioned. You can't do physics.
Isn't that unquestionable?
No, that's not an assumption. There's no assumption to be made when you say
you are making an assumption. If you're not
using an object, then you're not doing physics. That's not an assumption. That's just a rule.
No, because someone might question that and say, "I'm a physicist too," and I question that.
But it's not
an assumption.
But that's not an assumption.
It's an assumption in the sense that the other guy said, "Well, you're assuming that every transaction there's got to be some kind of object," and I'm not conceding that.
True.
So again, I put it as a principle, and another principle is the one that we just mentioned that. If you're going to cut a particle, or let's put it in different words, there must be an elementary or fundamental thing that comprises everything else. In the rope model, it's the thread. Period. We're done. We're never going to question that. We're not. If someone says, "What is it made out of?" It's not made out of anything because it makes everything else.
It's made out of itself. How about that?
Right.
It's like what's Ans made out of? He's made of Ans. How about that?
Yeah. It's a single. It's a single piece thread that makes everything else. We're done. That is the elementary.
I guess that's the right answer. It's made of itself.
Yeah, but that's like A equal A.
You gotta say
identity.
That. Where you say, okay, the apple is made out of juices. The juices are made out of atoms. Atoms are made out of the thread, and the thread is made out of the thread. Martin has a question or a comment. I hope I don't sound rude, but isn't the rope model greatest insight ever? By the way, like a little ad hoc explanatory for mathematical discoveries. I kind of use your model to discover possible architect.
Architectures, I guess.
Architectures for atoms and later molecules.
Yeah, I mean,
but for higher molecules, it gets really, really complicated.
I think what the rope model does, Martin, is gets people to open their minds and look at things from a different perspective. You know, I can't come to you and show you a real hydrogen atom and put it on the table. We can't see it. It's invisible. It probably forever will remain invisible. I'm not sure we'll ever be able to see.
You know what you do?
And all we can do is see it with the mind.
You do it like architects when they build a model of the building. They can't show you the building yet because obviously that's what they want to build. And so they show you the model,
the blueprint.
Yeah, the blueprint or the little model of it.
And all I can do is give you the blueprint and stimulate your mind.
To this same thing, I had a comment yesterday that never came up, which was about chemists. Because I think chemists will be the people to take on the rope hypothesis on board because it provides a foundation for them to explain in detail what is happening with chemicals without resorting to metaphor.
But they've got that already. They already have the rope model. Remember, the orbital model is the rope model, the balloon model.
Yeah, but
that's what the chemists
use it.
Oh yeah, they
but
use it.
They don't use it physically, literally. That's my point. It's
hold
a metaphor.
No. Well,
they always kind of cushion things.
Yes and no. Hold it. Yes and no.
The detail.
No,
of where the electron is and what the electron's doing. They always call it a bead within this orbital.
Yeah, but they don't use the bead. They use the bead. Listen. You got to understand how they really do that in chemistry. In chemistry,
they don't like the bead.
No. They use the bead when they have to use the the dot model. What is it? The stick and dot model. You know, when they have to show how the valence shells are connected, they'll put the dots and the little sticks, and they'll do all this stuff, and they say that's the depiction of the the dot and stick model. But when they want to really visualize what's going on there, what that molecule looks like, they use the orbital model and they use the orbitals. And you could go to one of these chemists and say, well, hold it, you're using the orbitals. I thought the orbitals are region.
Yeah, you're moving the path of the bead.
You're moving
the path of the bead.
Yeah, the bead already went, and you're taking his path.
He's wenting.
You know, it reminds me of Mighty Mouse. You know, in the 1960s, you had Mighty Mouse, and he would go around, right? And he would circle around a few cats, and with his trajectory, he would tie them up like with a rope. Yeah. And that's what these people are doing. They're taking the trajectory and turning it into an orbital. And now they're blending orbitals, and you say, hold everything. What do you mean you're blending orbital? I thought an orbital was a region. You're blending two regions, and they're aware of that, but they say, well, we don't understand Mother Nature. It just works. You know, when we do that, it works. You know, we get our molecule, we get our shapes of our molecule, we get that fine, but we don't know what this orbital thing is. And now, in that sense, you introduce the rope, and you say, look. What you've been dealing with all these years, all you have to do is forget about the word orbital and just call them balloons or shells or clouds, whatever you want to call them. I don't care. But they're real things that are blending. It's a membrane.
But it goes to what Martin said about you kind of taking on at least the most, what do you call it, unwavering or unchallengeable discoveries or observations that people make.
And giving it
with a grain of salt, because you never know how they saw it or what exactly went down. But usually, what everyone saw many times, you kind of take, okay, what is everyone observing or detecting or inferring? What are the conclusions everyone comes to the properties of light, magnetism, and gravity? And you say, okay, let's take these properties that kind of everyone came to and say, okay, how can we explain this in kind of an ad hoc way, but it's not really ad hoc. It's a 10-year ad hoc.
No, it also allows you to visualize. Above all, it allows you to visualize and give a new interpretation to what all these people have done in the last 100 years, because they've gone in there and they've measured and they've got all these equations. They've been banging supposedly particles in their chambers, and they can never figure it out. But now that you bring the rope model and you can apply it to what they did, it makes more sense because you can visualize it. That's why it makes sense. But if they keep talking about energy converting into mass, and then we have fields, then they lost you completely. You know, then they get lost.
I had a question about assumptions.
Yeah.
Is there a difference between the phrase "it's been established" and an assumption? Because you've used that phrase before, where you say it's been established that I don't know. Light has these properties, for example.
It's been established that this, if I let go of it, falls to the ground.
Yeah,
that's been established.
It's gone beyond assumption at some point.
Yeah,
there are things that have been done to death where you go, okay, we know this. We use the word "know" here. I don't know what the word. I don't want to define the word, but
no. It's okay because it means you can predict without error if you knew everything that's happening in the universe. Because if I let go of the pen and the asteroid strikes the Earth and kills us all before the pen falls, then my prediction did not.
Yeah, but it's not about predictions. It's more like going back to the know and pattern and all that conversation that we had like months ago. It's like there are things that you go, okay, we don't have to assume this anymore. We don't have to. I mean. Technically, if we're playing science by the rules, then you always have to use the word assumption. Okay, we're going to assume this, we're going to assume that. Even the things we know fall under
because there might be a religious individual in the audience says, "Well, I don't like your assumption."
Not even that. It's just por las dudas.
Just in case.
Just in case. For the doubts.
Yeah, cover all the bases.
So you always say assumption, but there is this kind of group of things that I guess the right way of seeing it is we all believe it. Like it's been established where no one questions certain assumptions. Like you'll bring forth even things that they've observed and they'll go, oh, we have a different explanation for that. They don't question the observation, they question how you interpret their observation. For example, like the CERN colliding two atoms. Okay, the observation has been made, you take on their observation.
And say, you didn't do that.
But that's different than things that have already been established for so long, like gravity, we have to explain gravity. Magnetism, okay, what are the properties of magnetism?
Yeah, but let me give you for instance.
Let me get real quick to a quick example for magnetism is the fact that opposite poles attract and equal poles repel. It's been established. We don't have to assume that anymore.
Yeah, there he goes. It's been established. But take light, light on light. One group, Burke's group there with, I think it was like 40 people. They determined that light beams do in fact collide and all the photons bounce out.
God, yeah.
But when you go into their paper, you read their paper, they established that with virtual photons. Photons that appear with a magic wand at the wish, at the desire, at the ad hoc whim or whatever of the mathematician. So anybody can do things like that. Let me just, before I forget, remember a couple of things. Not only do we have to explain, what we just looked at, which is the beta decay, and just in case here we have Dan's beta decay, which I stole from him, okay? So he put that out today and looks kind of nice, okay? He's showing how, again, the magnetic thread, the red one there, goes out, forms a shell, and then bounces back in, okay? So he did another take on mine.
Oh, that's awesome.
Yeah, so he built that one, and he stole that one from me. I'm going to sue him for.
You see how that uses superposition, because you have the red ropes, they're coiled around the blue ones.
Yeah.
But then they go through the blue one to go out.
Well, this is the way he sees it. The way I saw it,
there is no other way to see it.
Oh no, there is another way of seeing it. Let me show you.
Using superposition.
Well, hold it. This is the way I did it. I think I've got it differently. Which one is it? This one here. Here's mine. Look at mine. It's just sideways. Of course, he's got more like a 3D thing because it comes up. I'm doing it a 2D, so I'm showing that the the magnetic thread just peels out or rolls out of there. It kind of rolls out and becomes the electron shell.
Can they do that without going through each other? Or the other thread? Well, can you peel the ropes in this scenario without any thread passing through any other thread?
You would think that.
You kind of showed it with the rope when you pull them.
When the rope comes up, when the thread comes out.
When you pull them apart, right?
Yeah, I think you can. I know I would have to think about that, try to see if I can visualize it, but I think you can. Dan did it here. He did it like 3D. He's got the thread just going out sideways, and that way we can see the 3D mechanism. And Who knows? What I like about it is that he brainstormed and he saw it this way, you know, and that's good because we need a lot of brainstorming to find out, you know, how this thing works. So yeah, maybe this is the way it does. Maybe it's the way I showed it. They're very similar. And again, we have to explain why the mass of the neutron is just very similar to the mass of the atom. Okay, in other words, one proton plus one electron, a little what neutrino or anti-neutrino in there, you know, so on. So you got to explain that whichever model you go with. The other thing you have to keep in mind is which one was it? Oh, the orbitals. You know, as an atom gets bigger, these are different elements. And the bigger the element, the chemical element, the bigger the atom, so to speak, the more neutrons it contains. Okay, and there you see how it's you know, expanding because we're talking about different atoms there. Okay, and different elements. But what's the story? The story is that you got to keep in mind something, and that's why I'm saying you got to be very careful when you come up with theories or you know, different versions of this, because here you'll see something. Look at this chart. Not this one. That's not the one I wanted to show. I wanted to show, where is it? I didn't pull it up. Well, I guess I missed, oh no, I think it's part of this one, but this is the second part of it. That's what it is. So I'm going to wait till it begins. No, I didn't pull it up, I guess. Let's see if I can pull it out now. Give me a second here. I want to pull this thing up here. One more minute and I'll have it in here. This is what I want to pull out. There it is. I forgot to include it in my things here. And what you're seeing there is that that's the periodic table. And these are the sizes of atoms, the respective sizes.
Really?
Yeah. So even though you can see like lithium, that first line going from lithium all the way to neon, there's more and more neutrons as you go from right to left, but there are fewer and fewer diameters.
That's weird.
Yeah, and that's what you got to explain.
How has this been established?
They measured the diameters of the atoms, and then as you can see, as you go downwards.
Oh, that's awesome.
Yeah, and as you go downwards, okay, the atoms' sizes get bigger. Because from within each row, right, up and down row, I'm sorry, what do you call them? Columns. Within each column, the atoms get bigger as you go downwards, but they also get smaller as you go to the right. And you would say, well, what's the logic behind that?
I would have thought the opposite. That radon in this case would be the biggest.
Right, and then the explanation we have for that, and I do have an explanation, is the one you see here. And it goes something like this. Here's the sun. It squashes what does a star do? It squashes atoms. That's what it does. And there you see the atoms getting squashed and growing bigger. Okay. And as the electron shell expands, it incorporates more neutrons. Okay. Oh, I don't remember what the explanation for that was now. I'd have to look it up. But I do have an explanation for that, for this, you know, for how the atoms going from right to left get smaller, okay? I'm trying to think of what the explanation was right now.
Right to left goes bigger.
From left to right, I meant to say. Yeah, from left to right, it gets smaller, okay? The atom gets smaller, but it's got more neutrons.
it's
So if you,
heavier, isn't it?
it's
The ones on the
heavier.
right are heavier, denser, I guess.
It's heavier, and
Smaller.
yeah, it is denser. Oh yeah, okay. This was the explanation. I don't have it in images, so unfortunately, I'm gonna have to use words instead of the picture that is worth 1,000 words. But it goes something like this. Let's say you're gonna try to put 5 balloons in a box. Okay, you got a box of a given size, and you're gonna put in there, I don't know, 5 balloons. Okay, and now what happens? What's the next step? Well, now let's say you want to put 5 more balloons in there. What's going to happen to the balloons? Well, if you manage to fit them all in there, they're going to have to be smaller because they have to occupy the same volume. There's 10 of them. So the box doesn't grow. It's the balloons that get smaller. They get squashed. And so the question that we have to ask, okay, if the radius of an atom, and I'll put an example here, one of these, where is it? This one here. If the radius of an atom gets smaller, despite that it's got more neutrons, okay, you have this balloon in a box kind of situation where maybe the neutrons are getting smaller, squashed together with the protons. Maybe the protons get smaller because, see, they can tell you what the size of that neon atom is. The question is, what is the size of the protons? And you might say, well, a proton's a proton's a proton. Well, is it? I mean, when a proton forms part of a p orbital, and here, let me show you what I'm talking about when I say p orbital. Here's the image. Okay, those are the p orbitals just sticking out of there in figure 8s. So you have the round ones, which are the s orbitals, and those balloons that are sticking out, those are p orbitals. Well, what does the proton look like when it's a p orbital versus a round s orbital? You know, they have to take on different sizes or shapes. So do protons always have the same size? Do electron shells always have the same size? I'm saying they don't. And again, that's why the analogy of balloons in a box more or less is appropriate, because I think all these guys can change their shapes. The electron shell can change its shape, and that's what you're seeing there is the shape of the electron shell. These people say, well, what you're staring at is the region in which we can find the electron bead.
That gets weird.
But that's not a region, because a region binds with another region physically, and you can't say, oh, a region melted or blended with another region. No, we're talking about balloons. And so if these are balloons, and the balloon that you see there, the p orbital, looks different than the s orbital, which is the round one, obviously, you know, these balloons can change their shape, just like a clown's balloon. And when you have that situation, now it's easier to explain with the balloon in the box type of analogy. You put 10 balloons where you had 5, and now the balloons get smaller, and they can change shapes for all we know. You know, they have this ability. And so anyways, it's a little more complicated than that, but that just gives you a ballpark figure of what the explanation under the rope model would be. And then the other thing we have to explain under, you know, that's related to neutrons is this cosmic background radiation. If I see it, where did it go? It always, when it doesn't reach the top, it goes all the way to the bottom. I have trouble finding it. Okay, there it is. Here's the cosmic background radiation. Okay. And what are we showing there? We're showing what these people have measured as far as how the temperature or this radiation that pervades the universe kind of sizzles or vibrates out there. So they were able to map it, and this is their map. This comes from the WMAP expedition. A lot of people working on that project. And so we have to explain this, and you're saying, well, what's that got to do with neutrons? And again, under neutrons, we have to give an interpretation to this because under the rope model, we say all those 3-degree Kelvin radiation, all that radiation is really a whole bunch of neutrons. There are vibrating in space or through which light passes. And those are the nodes that we're detecting already. We have the ability to detect those nodes. Here's a picture of a little GIF there that you can see.
These are neutrons.
Yeah, these are neutrons.
These are not neutrons.
These are not. There's the neutron being made.
No. These are not neutrons.
These are not neutrons.
Yeah, these are what I would call neutrinos, or some other word, badangos. Because a neutron, to me, is a crossroads. It's a hydrogen atom without an electron shell.
Okay, that's what this is.
That's not what this is, because each one of these crossroads isn't a crossroads of all ropes.
Okay.
So there's a big difference there.
Well, hold it. But listen to something when you say that. Let me take this out so you can see how I get angry at my son here. I got a baseball back here. I'll whack him more. No, but look at this. Just ponder this for a second. And again, that's why you have to brainstorm a lot until you finally say, maybe I found the answer. So far, I can't say we have the answer, okay? But listen to this. Let's say if we take an average of neutrons. In other words, we go throughout the universe, right? Let's say we have 100 atoms, just a universe of 100 atoms. Yeah. And we have all these crisscrossing ropes. Wherever there's an intersection of ropes, we'll call that a neutron. Okay? Fair enough so far?
I'd rather...
No, hold it.
Let's call it an X.
Well, I'm going to call it a neutron.
Not neutron, but okay.
I like the word neutron. It's a beautiful name. Okay. We find these neutrons. I don't know how many there are. I'd have to do the drawing to find out. And again, you're talking about three-dimensional here, right? So these ropes are going in every direction.
How many crossings does it take to make a neutron?
Well, no. That's not the question. This is the point. Listen. So we have all these ropes that are crisscrossing somewhere. Okay? And now we take the average of crisscrossing. This guy has 10 ropes here. This guy has 7. This guy has 3. Okay, so we take an average and we say the average of ropes crossing, or the median or the mean or the mode, whichever number you pick, is 6. That's the average. That's what we're going to call a neutron. Everything else is a non-neutron. Hold it. Let me finish.
Oh, okay.
So we have, he already wants to
choke
me. I'm saying you have all these ropes.
Sounds like math to me. I'm going to get my pitchfork.
So we have all these ropes crossing, right? We take the mode, the mean, or the median. I don't know which number would be appropriate. And you say, okay, the number 6, where we have 6 ropes, we'll call that a neutron. Anything below, anything above, we're not going to call a neutron. And and we count these, and we say, well, not only is it the median, the mode, but it's like 90% of it. 90% of these crisscrossings are 6. There's only 2 that are, or 3 that are 3. There's 1 9, and there's 90% are neutrons. Let's assume that's the case, or something similar to that. Well, then we can say, look, the ones we detect, because they're just great majority, are these neutrons that have 6 ropes. And those are all around us, so we measure and we say, yeah, that's what we see. This neutron converts into an atom into a neutron. And so far, we're okay. The question Hans is asking is saying, if a neutron over here has a different number of crisscrossings, if this one only has 3, for example, what do we call that guy? A neutrino?
I make
invent more letters?
The differentiation that I make is between a crossing of all ropes and a crossing of less than all ropes. It's binary. It either has all ropes converge on this spot, but doesn't have an electron shell. So it's like an atom without an electron shell. That's what I call a neutron.
And those are the 6s.
Those aren't the 6s. I would say anything that doesn't have all of them is not a neutron.
Right, and that's what I'm saying.
Or we need 2 different words.
And that's what I'm saying. And let's assume that in our vicinity, right? Because again, we don't know what a neutron looks like or what an atom looks like between 2 galaxies in the middle of nowhere. But here where there's so much matter and there's so many crisscrossings, maybe the standard neutron that we detect is a 6. The 6 rope neutron. And that's the one I can convert easily into an atom into a neutron, no problem.
No, because you can't have an atom without all the connections. It's a logical error. So there's no such thing as less than all. They can convert back and forth.
And then I'll go back to my theory yesterday, or my assumption of saying, once a neutron, always a neutron.
Yeah, I'm saying there are neutrons, and then anything that's less than all never turns into a permanent.
We'll call it a muon or a pion.
These crossroads, they can show up on radars, but they're not neutrons.
Martin's got a question.
Yeah, Martin's got a good point, which is what I was thinking about.
Okay.
You see, when you and Dan present clips on H atom converting into neutrons and back, all I think is, how the hell did that happen? What made it do that? What keeps atoms in molecules from not doing that?
Well, no, the answer to that, Martin, is that we're not saying why did it happen. There is no cause in the sense that, God ordained it. He said, let the neutron convert into an atom. It just does. Whatever again, we're taking what these people do in the labs. Okay, they go into the labs, they do an experiment, they do whatever measurements they do, and they concluded that an atom turns into a neutron into an atom. Why? Because the neutron doesn't have charge, a free neutron doesn't have charge, and an atom does. And so they say they have approximately the same mass, and exactly how they came to the idea that this guy turns into this guy and vice versa, I don't know. But it's not a question of why does it do it. It's a question. It's like, why does light go at a certain speed at 300,000 kilometers per second? Well, it does.
I want to chime in on Martin's behalf, because this goes to the point of fixed amount of motion in the universe.
Okay.
Where any action has a reaction, that kind of thing.
Okay.
Where if something happens, there's a cause
Mr.
to it.
Isaac Newton.
Yeah. If something happens, there's a cause to it. There's some motion that was transferred in there for it to domino into some chain of events has to occur for this atom to spontaneously
but we're talking about all the
go
atoms.
down. Yeah. But there has to be some. For example, the pumping. There's a pumping going around in the universe, because this atom pumps, which makes the next atom pump, and it's like they're all pumping.
But then the question
passing on the pumping.
But you're
But where does you're asking on?
It's like, where did it start?
No, it's not where did it start. That's not the question, because this is a more specific question for what pumping makes the next pumping occur. That's just a domino effect. It's like a wave going around. But with this collapsing electron shell and then refilling electron shell, where's the precursor to that? The pumping is another pumping.
But it could be the same type of thing, where motion of what happens over there, pulls on a thread or pushes on a thread,
and it sucks in all the electron shell of this guy.
I would think that, why does a magnet have some threads come out? Well, it does.
Sounds like slack.
But they're aligned. The atoms are aligned.
It's like, what I'm saying is,
the atoms are aligned.
You have to account for the slack, or you have to account for the extra motion or energy, whatever word you want to use. You have to account for it. It had to come from somewhere.
I don't know.
Saying it just does, you're adding motion to the universe now.
Well, we're talking about causes here. We're talking about what caused this to happen, right? That's the issue. That's the question. And I'm saying, can we say what caused the light to go at 300,000 kilometers per second? No, it doesn't. But on the other hand, you can say what caused the goosebumps along the rope to get shorter. Suddenly you have high frequency and shorter wavelength. Something caused that, and we're saying, okay, we know what caused that. Under the rope model, you have faster pumping, so that slack turns into higher frequency. The release of that slack, that's what causes. So we do have an explanation for that. And in the same way, you're saying, well, now what caused the thread to pull back, right, to unwind itself and become the electron shell? What triggered it now to go in the other direction? Especially that it happens every 15 minutes.
Assuming it happens every 15 minutes.
This is what they measurements. I don't question in this sense, because they don't do it just once and say, oh yeah, we noticed. No, it's like something they verify over and over and say, look,
It's been established.
It's been established. It's like gravity. You let go of the pen, it falls to the ground.
But Martin's point is just about accountability, I think.
Well, yeah, he wants to know a cause.
But there is a cause. You can't really talk about a cause for light going at a certain speed. You could maybe.
Not the speed, but for the higher frequency, we have
talking about where could the cause of an atom shell collapsing or inflating come from?
And let's clarify one thing before going into more detail in that question, which is an important question, and that's the difference between cause and mechanism. The mechanism we can give you. We'll give you a mechanism. Say, look, the thread, the magnetic thread, pulls back and becomes the electron shell. That's what we think, and then when it goes inwards, it becomes the neutron again. The mechanism is there. Now you're asking, what is the cause? What caused that to happen? And what causes it to happen every 15 minutes? Obviously, there's a recurrent mechanism or process there going on, right? Going back and forth. And, I'm not sure we have an answer for that one. All I can say is some questions may not have a cause type, like the speed of light. No, the speed of light does not have a cause. It just is. But the frequency does have a cause.
I think the speed of light does have a cause as well.
Oh,
if you're talking about so much matter in the universe, well, when you talk about a parallel string thread, if you have another thread that's half as long as our thread, the speed of light could be higher or greater, or
in another universe.
But that's what I'm saying.
Yeah, but you don't know why. Why did God choose 300,000?
No. It just depends on the amount of thread that there is in the universe you're talking about.
We understand that.
In ours, it happens to be that number just because of the amount of thread there is. Right, you have to do the calculation to figure out why it is so. Why this amount of thread translates to the speed of light that we have.
I don't think you would be able
to
calculate
what Martin's talking about is you can't just kind of propose something and just say it is so. It's dangerous doing that. You want to watch out when you do those because at that point you're invoking matter.
No, you're not invoking matter. You're just saying I don't know. That's different. Quantum says I don't know, and so far, you're asking a question. I can say I don't know also. I can't think of a mechanism or a trigger for why that happens. It does happen, obviously, apparently, because this is what they observe in the lab. We're just trying to explain it. But is there a cause? Well, we have to brainstorm. That's all I can say. We have to think some more. And you're welcome to contribute as well to that question.
His last question.
Since you asked the question, you have now homework.
His last question is not really causes, more like what keeps the atom from not collapsing. But it's kind of the same question, just phrased differently, because it could just be that something's causing it to collapse. Normally they don't collapse, and something causes it to collapse, or normally they collapse, and in certain cases is not collapsing.
Yeah, the atom in a way is collapsing. Keep in mind that when the thread, let's assume that's what Mother Nature's doing. Let's assume that the magnetic thread really goes down to the center together with the proton, with the electric thread, and rewinds itself. And now you have ropes just crisscrossing in that region, and that's the neutron. In a sense, the atom has collapsed. And maybe that's why they say, suddenly the atom disappeared. And they say it just blinks in and out of existence. And what it's done really is turn into a neutron. So in a sense, the atom has collapsed. There is no more charge in that region. And yeah, that's some of these things we got to think a little more about. Anyways, this coming week, we're going to be on the road, and we won't have classes next week. So I'm going to have to say until the following Sunday today. And we'll see you then, same time, same station. Okay?
Preparing for November?
Yeah, we're going to be preparing for a trip to Argentina then as well. And so we're going to try to see if we can transmit from Argentina. There's going to be a couple guys over there. We might include them in our powwow, in our transmission. So we'll see how it works. We're going to take the cameras and see what we can do. We'll see you then. We'll see you in not this Sunday, but the following Sunday, okay? We'll see you then. Bye-bye.